If you're a cynic, and I am a cynic, you might object that data science is nothing terribly new. A lot of the things we're talking about in data science are old ideas. But I meant to look up the date data science as a term was invented, but it was sometime in the last decade was the first time anyone talked about data science being a thing. But I think that's overly cynical. And this is coming from me as a cynic. There is something about data science that's different from the things that came before. And as I see it, there's two fundamental components to data science that both existed before data science was a thing, but by combining them, we have something that is new and unusual. And those two components are machine learning and distributed computing. And I'm going to be trying to give you some of the words you see as we talk about these things without actually getting into too much depth about what they are and how they work. But the basic idea of machine learning is it's model building. And you've probably built models in your schoolwork, in your career as well. For example, I'm sure you have some sort of sales model. You say, what we expect to sell next month is about what we sold this month, plus, I don't know, maybe an extra 10% because we just brought a new salesperson on. So that is a model. You've built that. You've fit it off of your old data, and then you can use that to make predictions. So what's different about machine learning models is that they are very complicated, very flexible, and they don't include sort of any domain knowledge necessarily about how you expect things to behave. So for the machine learning model, you type in last month's sales and the last year's sales and the number of salespeople you have and the phase of the moon and Apple stock price, and all of these things go into it, and it will come up with some prediction based on those. And as you can imagine, this is going to be pretty complicated. So many of the machine learning algorithms that we teach are things that were theorized about back in the 60s and the 70s. And it's only in the last 10 years or so that we've had the computer resources necessary to process them. And these algorithms tend to become most powerful when you can learn from, or the sort of nomenclature of machine learning, train on a lot of data. If you only have 2 months worth of sales data, all of these flexible models aren't going to help you. But if you have years of sales data that's split down by individual targets, individual salespersons, and so on, then you can get a powerful model out of this. So that's sort of one side of data science. The other side, I didn't know exactly what to call it. So I'm calling it here distributed computing, but quite often it's referred to by the thing that we actually have, which is big data. And by big data, if you've been to the TBDS class, you've probably seen the volume, variety, velocity, the 3 V's there. And it's just describing the fact that we have so much data these days and it comes at us so quickly. If like me, you grew up on floppy disks, right? They came with 1.44 megabytes of storage. Now I have this little USB drive that is, I don't know what it is, 32 gigabytes. So up by a factor of 30,000, something like that. A lot more data now. And before I was dealing just with text, basically, text documents, these things. Nowadays it's video and images and audio and all of these types of things. And it's coming so much more faster, right? Processing a gigabyte of data is not terribly hard, but if you have a gigabyte coming in every minute or every second, then you really have to think about how you're going to handle that. It does you no good to parse that gigabyte in 2 hours if you're getting a new gigabyte every hour coming in. So that is big data, and specifically distributed computing comes when you have too much data to fit on a single machine. And there's a little dirty secret that I'll let you in on here, which is that a lot of people who think they have big data don't actually have it. Because nowadays you can actually buy very large machines. So I was just noticed a couple weeks ago, you can buy a single computer with 12 terabytes of RAM. a terabyte being 1,000 gigabytes. That's a lot of RAM. That's a lot of data you can store on a single machine. So if you're Google or Facebook or Amazon, yes, you need big data. Many other people don't actually need these techniques. You can deal with it, these huge amounts of data on a single machine. That said, if you have even less than a terabyte, still, you probably need high-powered tools to understand data that's coming in at that scale. And this is what that arrow is trying to represent, that these two things feed on each other. To get a powerful machine learning model, you need lots of data. And to understand lots of data, you need powerful models. So it's this sort of synergy that I think actually makes data science into something new rather than just assembling existing parts. So machine learning is generally split into 3 different groups: supervised, unsupervised, and reinforcement learning. These are just changing exactly what it is that you're trying to predict, whether it is reproducing a known value, exploring some data, or trying to train a process to accomplish some task. In terms of even doing machine learning, there's differences between these, but it's not quite as large as you might expect. In talking about machine learning, most people are going to have to do at least some of both the supervised and unsupervised machine learning. Reinforcement learning is a little bit of a special case and one that we actually don't currently teach, although I'd love to put a class together about it. As sort of an aside, you'll hear people talk machine learning. You also hear people talk about artificial intelligence. And there are plenty of debates about what these things actually mean. But a relatively good definition is artificial intelligence is just the field of making computers look smart. And machine learning is one way to do that. It's sort of the most exciting method, at least right now. That's where a lot of the interest is going to. So a lot of people will speak of machine learning and artificial intelligence as being synonyms, although sometimes artificial intelligence is referring to a larger field of which machine learning is just a part. How do we do this? Well, this is a, whoops, sorry, I got ahead of myself. What are we doing with machine learning? In general, there's going to be 3 types of projects that you take on, and sort of in order of increasing complexity. I like to call these descriptive, predictive, and prescriptive projects, which are just going over the sort of the set of possibilities here. You can be describing what happened. And so descriptive machine learning is just, can I understand this data I already have? Predictive is, okay, given what I can measure, can I predict what's going to happen in the future? And then prescriptive, given that I have some ability to look into the future, what should I do to maximize whatever this thing is that I care about? And basically, you can't do a prescriptive project unless you have some ability to predict the future. You can't predict the future unless you have some way to describe what's going on now. So these build on top of each other. But you don't necessarily have to get to the top level. You don't have to get to, top level is on the bottom here. You don't have to get to the prescriptive layer in order to have success. We'll talk about this a little bit later, but oftentimes there's a lot of low-hanging fruit even at this descriptive layer. We have all this data coming in, nobody has looked at it. What can we gain just by trying to categorize this data we have rather than trying to make predictions or make suggestions for the future? Oops, and now I think we can get on to another one of these lots of words slides. There's a bunch of algorithms out there to do machine learning. Sometimes people say, I want to learn machine learning. Sometimes they tell you, I want to learn X, where X is one of these algorithms. So I have these here just to start getting used to some of the terminology. There are algorithms like linear regression and decision trees and random forest and gradient boosting. These are all just ways of doing machine learning. I put things like clustering and dimensional reduction in there. These are not algorithms per se, but they're common tasks of machine learning. And if people are talking about these, again, they're just talking about how do I do some of these basic machine learning tasks. So all of these are example of what I would call traditional machine learning. And these are algorithms that have been used, as I said, some of them dating back to the 60s and the 70s. And many of them are strongly motivated by something from statistics, especially things like linear and logistic regression. We can prove under certain statistical assumptions that they do the right thing. Many of the exciting things out of machine learning in the last 5 to 10 years have come out of the field of deep learning. You've probably heard that buzzword. You may have also heard of neural networks or artificial neural networks. They're all referring to about the same thing. Again, people can quibble about the exact borders and definitions, but for our purposes, think of it as the same thing. And what these are very powerful and flexible models that as a response take a lot of time and a lot of data to train. And we're getting a lot of cool results from these recently, largely due to sort of historic accident. Powerful GPUs that people have been building to make ever more realistic video games turn out to do the same sort of math that you need to do to solve these neural network models. Just happens to be sort of an accident. So the fact that we wanted to be able to pretend to shoot other people realistically allows us to solve these very complicated models. And the interesting thing about these is that deep learning models have the ability to keep learning efficiently as more and more data are added to them. So I've tried to sketch out here just a rough idea. As I add more data to my model, how much better does it perform? And traditional machine learning will learn quickly, but then start to fade off. There's only so much data you can put into it and it can learn from. Whereas deep learning will often not do as well on a small amount of data, but they sort of keep improving as you add more and more data into the model. This is sometimes been called the unreasonable effectiveness of data. And people will debate why it works, but it does work. So lots of the interesting results in self-driving cars, machine translation, Google Assistant are all deep learning results taking advantage of this. So here I have a couple of the tools that you see people talk about using. Again, you don't have to know the details of what these are. I just want you to not be afraid when you start seeing these names out there. So scikit-learn is one of these standard machine learning libraries. It's the thing we use throughout our curriculum. And when I talk to people out there in industry, everybody uses this on that exploratory side of data science, where they have a problem and they just need to start trying to figure out what's going on. Not used for production as much, but definitely used in exploration as well as in teaching. Some other things you'll see, XGBoost is a particular algorithm. It's won a lot of these Kaggle competitions, or I should say specific uses of it have won a lot of these Kaggle competitions that you may have heard about. Spark ML is doing lots of these machine learning algorithms in distributed systems. We'll talk about Spark in a little bit. TensorFlow, PyTorch, Theano, Caffe are all neural network libraries. As you can see, they're coming from different tech companies or from academia. H2O is a company that offers essentially this machine learning as a service. They were one of the first to do that. So you give them some data, they try to figure out how to do machine learning on it and give you some results. They're trying to get to the point where you don't have to understand what's going on, but I think that's sort of dangerous. And this last one is a little bit of an odd man out, but ONNX is an interchange format, a way of describing machine learning models. And we're seeing that at least some people start asking about this. It's not something we currently teach, but this is something we need a solution for. So hopefully this will be it and we can add it to our curriculum. So some of the tasks that people might want to be accomplishing, these are things that you will probably hear people talk about. Natural language processing is understanding human language. People have this annoying tendency not to speak in nice, clean SQL queries. So understanding what people mean from what they say or what they write is natural language processing. Image processing or computer vision is all about given an image, what's in there, what part of that image is the object you care about, what part of that image is background. Time series analysis, that's any task, any machine learning task where the past will influence the future, which is quite a lot of them. How can I use that past information to predict what's coming up here? A couple different names for basically the same thing: anomaly detection or outlier detection or novelty detection is all trying to understand, is this data that I'm seeing right now the usual data, what I would expect to see, or is it unusual in some kind? Recommendation engines are trying to match users to products. So when you go on Amazon and they tell you you should buy these things, there's a recommendation engine behind that trying to figure out what you're going to buy next. Churn prediction, if you have any sort of user base, trying to understand which customers you're about to lose, that is sort of a very common task, and it's much easier than trying to figure out which customers you'll be able to gain. There's lots of risk assessment you can do with machine learning, and also a lot of just optimization problems, right? I want to do something by modeling the cost to do that, whether it's in time or money or efficiency, I can try to figure out what the best way to do that is. I'm not going to go into quite as much depth on the distributed computing side of things, in part because this is a little more sensitive to exactly how you are doing your production systems. But the basic idea is that I can speed up a repetitive task by having many computers all do a part of it all at once. I would rate this as a subset of parallel computing. Parallel computing is in general, how can I take a problem and run it on many computers? And by distributed, we're usually talking about those that are easy. Sometimes the embarrassingly parallel name is used, where you don't have to have a lot of crosstalk between the different parts of your solution. So a couple examples might be processing a bunch of records. You want to do the same sort of processing on each part, calculating a lot of statistics. You can calculate sub-statistics on different parts and then combine them. Or even training a model. It depends a little bit, but a lot of machine learning models are relatively easy to parallelize their training process. This is, as I mentioned before, you don't need to have one computer spend a century or a decade training. You can have 1,000 computers spending a couple weeks on it. Some of the tools you're going to run into here, and this is going more or less past the future. Hadoop is an old framework, but still used a lot, mainly just trying to organize a bunch of computers or a cluster of computers, allowing you to run a single task across all of them. MapReduce is an early library for distributed computing, and in most cases, it's going to run on top of Hadoop. We used to teach this in a fellowship, but we got rid of it because nobody was looking to hire somebody who had MapReduce experience. Currently, probably the most popular distributed computing framework out there is Spark. It can run on top of Hadoop, but it doesn't have to, and I won't get into all of those details. It's very popular. It's probably the framework to use for distributed computing these days. It's written in a language called Scala, but there are bindings that let you actually write your code in Python. And some people will just call that Spark. Other people refer to this as PySpark. So it's the same project, just a different language to write your code in. Before I move on, that's all I was going to say about distributed computing before I give you a little view of some other terms that you're going to run into in the data science space. I've mentioned a little bit, but Python is a very common language used for data science. It's named after the comedy troupe, not the snake, although the logo is the snake. I really like Python myself. I'm happy to use it. I'm happy to teach it. I would say it is a slow but expressive language. By that, I mean it's not terribly efficient. It'll take a lot longer for something in Python to accomplish the same task as some other languages. But it's very easy for me to write what I mean as opposed to worrying about all the other things that you might have to worry about when you're programming. It comes with a huge library of tools for it, especially for data science, but really for almost anything you want to do. There's a library for Python that does the hard work for you. Inside of this, I've just listed a bunch of different libraries that are Python libraries that you'll use inside of Python. So if you run into somebody saying, oh, we need to learn pandas, that's not another programming language, it's just part of Python, but it's very common in data science. Another relatively common language is called R. And this is a language where Python was designed as a general purpose scripting language. R was designed specifically for managing data. It's very popular with statisticians and for some reason biologists. I'm not quite sure how that happened. There is some usage of R in the data science community, but it's not nearly as large as the Python community. We used to have some R curriculum. We've dropped it because there wasn't a whole lot of demand, but it's still sitting there in our history. SQL is a language for interacting with databases. It dates back to 1974, which is pretty impressive. And it's still very much in use today. Arguably, if you go out and look for job postings, SQL is probably the most demand language, certainly in the data science space, possibly even out there beyond. I mentioned Scala. It's built on top of Java, which is a very popular enterprise language. It's going to be faster, but a little bit less expressive than Python. It's notable mainly because it's used for Spark. JavaScript is the language of web browsers. It's not actually related to Java, despite the name, completely separate languages. But it's useful for data science because many modern visualization tools use the browser. Instead of trying to build the whole UI, they just have something display in the browser. So you may need to know a little bit of JavaScript as a data scientist. Tableau and Alteryx, unlike the rest of these, are sort of closed source or proprietary toolkits for data manipulation. They're gaining interest, it seems, especially for people that don't want to spend as much time developing their own tools. And the last thing I have here are a couple very low-level languages, C, C++, and Fortran. These are old, very high-performance languages. You probably won't encounter them too much in data science. Occasionally, you need to dump down into them if you're trying to put something into production and you need raw speed. So the last thing I think in the presentation, if I remember all the parts, is just talking a little bit about, okay, what does this actually look like in practice? I've told you what data science is, why it is different or new, but when you're actually doing it, what does data science look like? And everything we've talked about up now is sort of in this middle part, which I've labeled here as model building. And that's the cool thing that everybody wants to talk about. But honestly, it's like 10% of the whole data science pipeline. The majority of the time of a data scientist is probably going to be spent on what I noted here as data wrangling. You also see it called data cleaning, data munging, ETL for extract, transform, load, or feature engineering. There might be slight differences between these terms, but all these are about getting that data in, cleaning up missing data or incorrect data or corrupted data, merging data from two different sets that use different ways of identifying the same objects. This is a lot of the work that's being done, and it's absolutely crucial for the rest of this pipeline to be useful. So some of the things we've talked about before, things like Python and pandas are useful here, but there's also just a lot of elbow grease and WD-40 and duct tape and whatever you can grab to try to solve these problems. Once you have the data relatively clean, then you can go into that cool part of building a model, training it on a lot of data. It may take a long time if it's a deep learning model, but that's not time that the data scientist actually has to sit there babysitting. It's just, okay, I'll let this run for a day, and then I'll see what it tells me at the end of that time. It may not even have to involve machine learning. You could be doing some simple descriptive statistics at this point and still get benefit out of it. And then finally, all of this is useless unless you're putting this into production. I think this was the point that was raised earlier. Yes, we can do all this work, but until you are giving something usable out of it, it's wasted work. And this can be everything from just giving a presentation. Here's what we found, and therefore we should change this business practice in this way. All the way up to, we're going to put this model in production and it will automatically serve ads or make recommendations. So this is sort of a wide range of possibilities here, and it really is going to depend on the problem that you're trying to solve. And I think it's also worth talking about who is going to do these different things. And that depends quite a lot on the company and the size of the data science team. It could be that your data science team is one guy, in which case they're doing all of this. They're bringing in the data, cleaning it, manipulating it, storing it, building models, and producing a website or a service that you can access. But as teams get larger, as the company grows, as the data science teams get larger, you start to see some of these other names pop up a lot. And there's no established nomenclature for these things. There's no official definition of what all of these roles are. So it will depend a lot on the company. But in general, a data engineer is going to be somebody who handles the beginning of this process, bringing the data in, cleaning it, and they may also be worried about how do I store this in a way that helps us access it later on. Typically, a data analyst will be somebody who's doing early analysis of the data, probably not building complicated models, but doing statistics and maybe some simple model building on this. A machine learning engineer may be involved with model building. They may also be involved with taking a prototype model and then turning that into a production level model. And by the time you're developing sort of production, you may be dealing with a developer, a software developer, or even a DevOps person as you're trying to put these things into a live production environment. You're also going to see a number of other titles for people who are doing data science-y stuff, just depending on where you are. So a lot of data science is filling in business intelligence or business analysts. So sometimes people doing these things are going to fall under those names. In finance, they may be called quants or quantitative analysts. In banking or pharmaceuticals, they might be called statisticians. Insurance, they might be called actuaries, but they're all probably using similar models and a similar pipeline to this data science pipeline. So this is a slide with some terminology that I just made up. So don't use this and expect everyone to know what's going on. But as I talk to companies that are doing data science, I sort of see it's really a continuum, but with two endpoints. Whether the data science they're doing is evolutionary or revolutionary. So by evolutionary, I mean they're taking an existing process and they're making it better with data science. So for example, with marketing, now you can market not just to an entire city, but down to an individual with all these demographic informations. In contrast, a revolutionary use of data science is building a product that's only possible because you have data science. So the example I give here is self-driving cars. Data science hasn't made the self-driving car department of Google better. It made the self-driving car department of Google possible. So these two types of applications generally have different use cases, different needs from what I can tell. So in the evolutionary case, the people doing this may not be data scientists. They may be analysts. They may just be engineers who have realized they need the tools of data science to make their job better. And as a result, a lot of the gains to be had are going to be in that early stage, that data wrangling process. They have all this data, they simply have not analyzed it. The people in the staff may not have any data science experience at all. They may only have small amounts of data science experience. Well, they do have a lot of domain knowledge because they've been doing this job already without data science for years. And they want to figure out how they can just leverage these tools to make themselves better. And as a result, when you ask what they need to learn, they probably tell you stuff all over the spectrum of subjects. They may need to learn pandas and Python. They may want to learn some sophisticated deep learning approach, but generally, any of these are valid targets. Whereas a revolutionary team, a revolutionary data science team, is probably staffed with people who already identify as data scientists, and they need that full pipeline working before they can get a benefit, right? It's not like they can improve the business just by having better understanding of their data. Their business is the data science product. So the people they hire are generally already data science experts, and when at least I've talked to them and want to know what they want to learn, they have very specific algorithms and tools that they want to be taught. Historically, our training has tended to be with teams on the evolutionary side, people who have existing business processes and they want to improve them with data scientists. For hiring, we see companies of both types. We see companies, traditional, long-standing companies that are trying to build up data science capability, but also innovative companies that have been formed to do something that can only be done with data science.